don't, my name is Dan O'Boyle. I'm with Burt Process Equipment. I want to thank Jim for getting me in front of, and my sales manager is Dave Carson. He's going to be doing this presentation today. But I want to thank Jim for getting me in front of you guys. I know we've tried to do this maybe a year or two ago, and we're finally getting around to doing it.
Maybe you want to thank these guys later.
Yeah, right. See how it goes.
Yeah.
Thank you at 3 o'clock.
Yeah, well, I was with two of them. They're not too bad. So, I live outside of Reading, so I'm pretty close to you guys, at least here. And Williamsport, I get up there probably once every week and a half or 2 weeks or so. Yeah.
You don't believe him?
Yeah.
I think all reports.
Yeah, I started with Burt about 3.5 years ago, and I came in here and met with Jim, and he gave me everybody's contact information, and I sent it all out, just seeing if we can, like we're trying to do now, do some business together. And at that time, I was a little green to the industry and to obviously new to Burt Process, but I didn't really follow up on it as well as I should have, I guess. But my goal is to have you guys out in the field, and that's why we're having this pump training. You're in all the different places that that uses pumps. I mean, you probably see it all the time when you go into these places. I don't know if you're asking the questions on what they're doing with their pumps. I know you guys are always more concerned about pipe valve fittings, things like that. But moving forward, and after this training, hopefully you guys will begin to at least understand a little bit about the different types of pumps, how they operate, maybe be able to answer some basic questions on pumps, and try to, the most important question to ask is, who do you buying the pumps from, or can I help you with an application more so than not, and try to just get that business into the office, have Doug or whomever quote it, work with Burt Process and myself, Lanny and guys like that who can really, as you know, help you out with any technical questions you have. I've worked with John and visited a couple of plants and also with Vic, and came in as a representative for IPS. Looked at some applications. We have a trial pump going into Conagra, arrow pump, a diaphragm pump. What we're going to try to do is work on pricing to make it more competitive, so that we both can make some money moving forward, so that you're competitive with whoever is currently selling your customers, and really work on this so that we all can make some money and we get the opportunities. And obviously it's up to you guys to go out there and ask the right questions and get the opportunities, and bring me either on site or get Lanny involved with technical questions. We brought actually the hour rep down to Conagra as well, the manufacturer rep. So we can do that. Flux, we can get Tim down here for Flux, and he can go meet these guys. So don't be afraid to use our resources and myself to get out there and really push the product. And it's easy, it's hard to get out there and try to push something you're not familiar with. I've been there, I've done that. And you shy away from those type of opportunities. And I guess hopefully moving forward from here, you'll have a better idea, and you won't be shy to ask the questions and to move forward with trying to get opportunities. So, with that said, I'll turn over to Dave, and we'll start the training. Any questions you have? I know I had asked Jim to see if you guys had any applications that you could bring here. Dave's can go over any of those, give you solutions, and then we can work on whatever pump or pricing that you need. Yeah, don't be afraid to ask any questions through the training. Dave?
So, thanks, Dan. So I put together a presentation basically going over the basics of pumps, starting with centrifugal pumps that going into rotary positive displacement. How much are you guys familiar with pumps? Have you sold pumps?
There's varying degrees of obviously you can sell a pump, but then having a problem with the pump, figuring out sizing the pump is something different. So some of the guys are comfortable sizing the pump. Some of them have no clue even how to size a pump or read a curve chart.
Okay.
And then we have Vic, who just is.
I didn't even know there was a size.
Didn't even know how to spell pump. So
But you know where to
So
go to
just
find the
through
information.
basics. I
Who
think
to
it's a good
ask.
refresher course on, I think it's just good,
Yeah, so for some of you, it might be a little remedial, so bear with us. We'll get into other aspects that you might not know. I think, a couple things. You guys are all in sales. 90% of it is about relationships. You have relationships out there today that people are buying pumps. And it's an additional avenue for you guys to increase revenue and earnings for yourself and your company. So I see that definitely the value of this presentation and sharing this information. But anytime I do training, it's very easy to talk about features and benefits of an individual product. That's the easy part. But understanding the core technologies of what the equipment is, why it was built and designed, allows you to have a better understanding overall. And that's really what I try to focus on, at least with my salespeople, and getting them to understand the core basics of a technology. So I'm going to start off with basic centrifugal pump. The goal of any centrifugal pump is to add pressure to the fluid by increasing its velocity. We do that by centrifugal force. Basically, how we do that in a centrifugal pump, the fluid comes into what we call the eye of the impeller. The impeller rotates this way. A lot of people think it scoops. It doesn't. Fluid comes in and it rides on the back of this impeller vane. It actually gets flinged. We fling it, we generate centrifugal force, which goes up through the casing. And I can kind of show you when I get another slide, also on this demonstration. So we have the pumps rotating this way. It gets picked up. We force the fluid around on the walls of this casing, off of the back of the vane. We fling it to the wall of the casing. It comes up. We have what's called a cup water here that forces the fluid up through the discharge, and it doesn't allow it to recirculate into the casing. So essentially, that's how a centrifugal pump works. Now, based on your size of your impeller, your suction and discharge, which is known as the infinity laws calculations. You can calculate your size of your suction, discharge, and impeller, and your speed, and figure out how much flow or how much pressure you can generate. So these, you could increase to an 18-inch impeller and be able to drive that much more pressure. Or they do other things like stages. So a pump could have multiple impellers. So that way your flow remains the same, but you're able to develop a higher rate of pressure. We'll go into some of that. So as I was discussing, here's just to recap. So the fluid enters your suction, travels into the eye of an impeller, like we discussed, rides that back impeller vane. We impart centrifugal force. Then it rotates around your casing. The majority of the water goes up through the discharge as it's riding on the inside of the casing, and the remaining gets forced through our cut water, or also known as a casing tongue. So centrifugal pumps can be subcategorized. I mean, all use centrifugal force, all have the same property, but every principles. But we can subcategorize it by the impeller type, and even within those types, we can then further subcategorize centrifugal pumps by their impellers. So the subcategories are radial, axial, mixed flow, and peripheral impeller. One of the most common, most popular by far is your radial flow centrifugal pump. It uses solely centrifugal force to develop pressure. Radial flow pumps have three common impeller types. These are open, semi-open, and closed impellers. A closed impeller is your most efficient. You can see there the third one over. You have basically you have this impeller here, but you have a front shroud to it. And the shroud's compressed right here, and you actually have then an opening for where the impeller eye. Okay, That allows us to generate the most pressure. Some of the hiccups though with it is solid handling. You're not typically gonna get much solid handling out of a closed impeller type, okay? Then you get into a semi-open, this is a semi-open impeller, where now your front shroud's removed. You're not able to develop as much pressure with this design, but now you're able to handle some basic solid laden fluid, smaller percentage and whatnot. And then you got your open impeller design. Again, less pressure you're able to develop with that, but now you're into being able to handle higher solid lading fluid. And a lot of times with your open impeller, they take, if you see on the edge, they take that and they'll make a blade out of that. And you ever hear of your chopper pumps and stuff like that? I mean, basically start slicing through branches and a lot of other stuff. So that is your three main, and you'll come across this, at least in the centrifugal world, more than any other pump technology. The next is your axial flow. Basically, they call this this design the propeller pump. It looks like a boat propeller. Basically, some of the key applications that you'll see a mixed flow pump on. Ever go to an amusement park and do that water ride where you're in a big tire with all the seats around? Mm-hmm. So basically, this design allows us to move large amounts of fluid, but at a relatively low head. So on that ride, 90% of that's gravity. So we're probably taking 55 to 100 or 200,000 gallons per minute and going up 10 or 20 feet for that ride to work. So the other thing is that this pump doesn't solely use centrifugal force. Well, it does generate centrifugal. It also, the vanes itself actually push the fluid. So you have two aspects on this one. So your next is your mixed flow, and basically it uses both technologies, the actual flow as well as the radio flow. It's usually set up, these pumps are set up on a 90-degree angle. You'll see these applications in these pumps in large HVAC pumps, where we're moving like cooling tower water or larger flow, larger pressure applications. A lot of power plants, irrigation, irrigation applications. So we will see the majority of those. The next one, and one of the more interesting pumps, is your peripheral. Majority of people call it a regenerative turbine. So the issue you have with a centrifugal pump, just by nature, is you're stuck. You're stuck on certain size. This impeller is a certain size. This casing is a certain size to produce a certain amount of flow and pressure. So the hiccup when it comes to a centrifugal pump is your low flow rates and your higher pressures. Because what do I do then? I need a casing this big and a impeller this big for a very low flow. It doesn't work. I'm fixed on how much this rotates. So what they came up with is basically a hybrid between a centrifugal and a positive displacement pump. Let me get up there so I can kind of show you guys how this works. So basically, the other known name for this is a vortex pump, and basically what we're doing is we're creating two vortexes in the fluid path. If you let me come over here first. So what we have is we have this interesting impeller that basically just has multiple vanes on an edge. We get our two casings where when we pancake it together, generates this very small channel, okay? So we force the fluid in this small channel, and then we create the vortex. Now you guys, canoe, put your paddle in, and you see the vortex created in the water. essentially we're doing the same thing, and we're imparting energy into those vortexes as the impeller rips around that small channel. And what that does is it allows us now to be able to do a couple of gallons per minute, all the way up to hundreds of feet and hundreds of PSI in discharge pressure we can develop. So it's an interesting, different take, and it really secures a niche application where a traditional centrifugal pump would not work. So some of the applications that you see on this is, again, water boosting, recirculating, cooling, heating fluids, those type of applications. And when we go into centrifugal pumps, there's two main configurations. There's frame mounted and closed coupled. So frame mounted uses an internal bearing frame assembly that includes a lubricated inbound and outbound bearing connected to a drive shaft and then fixed to an impeller. The drive shaft's connected to the motor shaft via a flexible coupling and a line. Both pump motor are then mounted on a base plate. So we get into the pump. So this is your typical frame mounted pump. So basically on this back half of the pump is what we call your bearing frame. This housing holds your inboard and outboard bearings. Internal to this, we either put lubrication, grease, or oil into this housing. There is lip seals that protect from the fluid to getting into the pump or leak out on either side. And then we get a mechanical seal right here. This is the space in which the mechanical seal sits in is called the stuffing box. We'll kind of get into that. The reason it's called the stuffing box is back in the day with boats, they actually, when they put the propeller through the boat, they actually built a box. They took the box, drilled a hole for the shaft to go through the box, stuffed it with fibrous material, a little bit of lubrication to seal it out. So that terminology has maintained into the pumps as well. So this is the part that we're talking about. And then whenever you have a frame mounted, what we have to do is we have to align it. We're going to put it on now a base plate. We align the pump end and the motor, and we put in the flexible coupling. And then this is a representation of the guard. OSHA requires that we guard any rotating piece for safety reason. So the next is a closed coupled. You can see here, sorry for a bunch of the verbiage, I didn't know how to break that down, else I would have. So you can see on the closed coupled, we don't have that bearing frame. That bearing frame is replaced by an adapter. And that adapter would be right here. So your rear adapter with a foot on it. Some of them are more elongated. This is a little bit more compressed. But what that does is it eliminates my inboard, outboard bearing, my whole bearing frame assembly. So for a pump manufacturer, it's a lot less expensive. I don't have to worry about alignment issues associated with the frame mounted. Space. Some customers don't have space, so it actually shrinks down the size. So what we're doing is now, instead of having your typical frame motor or T-frame motor, we replace it with a C-face motor. What a C-face motor does, it has a polished front that allows us to mount everything up to the motor. So you see here the bell housing has holes. So that's already provided by the motor manufacturer. So we bolt this assembly on. And typically, there's two setups. There's your C-face, and when you use a C-face motor, we get a stub shaft. The shaft actually fixes onto the motor shaft, and your mechanical seal and your impeller all ride off of that stub shaft that's connected to the motor. Okay? On a JM frame, we talk about the JM frame. So the motor manufacturers recognize, hey, guess what? all these pump guys are using a stub shaft, right? So the sales guy went out one day, said, I can make more money if you take that shaft, elongate it, thread the end of it. So that way now they don't need a stub shaft. You get a JM frame motor, and you use that elongated shaft to put all the components on it. So in that case, this shaft here would be threaded, and all the components, rather than having a separate shaft, all ride onto the motor shaft. So again, for the pump companies, it's a lot less expensive. Don't have to worry about alignment issues associated with frame mounted. So that's basically the setup about the closed coupled and the frame mounted. So let's talk a second. So we're taking the inboard bearing and the outboard bearing assembly, and we're transferring that wear to your motor. So there is some negatives in that. Typically, a frame-mounted pump is much more robust, will last longer. The cost is considerably more money. So there is advantages for a customer to want to go with a bearing frame. If you got a heavy industrial application, so those are some of the things and some of the discussions that we have with clients is, are you sacrificing the robust for cost? Do you understand that when you have issues with a closed coupled that has everything riding on the motor, maintenance, basically you gotta take the whole pump apart because everything's on that motor, where, might not be the case. And the biggest issue that you have in centrifugal pumps, and we'll get into this on the curve, but as we start moving away from what's called the best efficiency point, and I'll get into that for you guys what that is, you have what's called deflection. And what happens is when you have deflection, you have vibration. When you have vibration, that impacts wear on your bearings. So it's something that we want to take care of. So that's the two basic configurations. So let's talk about sealing and sealing methods. So, most rotating pumps require some sort of a sealing method. The three most common are packing, mechanical seals, and sealless magnetically driven pumps. So, I have a seal here on this pump, but let's just recap what I was telling you before. Here's where your mechanical seal is. Everything's sat in this stuffing box. We also, instead of mechanical seals, we can use packing. And packing is just kind of like what I was explaining to you in that stuffing box for the boat. It's a fibrous material that's used. So it's it's weaved fiber material. You can get them in rings, pre-cut or not pre-cut, could come into a roll. One of the Chesterton makes it and makes them, and several others. So what they do is they get this fiber material, they dip it in lubricants, coatings, and different materials to help whatever process fluid you're pumping. One of the most common is like a carbon graphite or PTFE, Teflon coated. We also do like graph oil, which is for high temperature applications, a lot of hot oil pump applications. So basically what we do is, here's your actual stuffing box of that area that I showed you on the pump before. So we take this, we stagger the cuts on the lines, and put that to the stuffing box. It rides around that shaft, and it actually uses the fluid that you're pumping to lubricate the packing and swell and take up that area, that cavity. And once you have a seal, it stops it from leaking. The only issue that you have is it inherently leaks, drips. Startups, single use, or intermittent use pumps, you're going to have leaking and whatnot. Not bad on a water application. Hey, I'm in a municipal plant and I'm pumping water, you know, you probably don't care. Or chemical or, you know, something else, that's a potential problem. But that's packing. Well, then we get the more common today is your mechanical seal. Mechanical seals have 4 primary functions. The first is your primary sealing surface. Then it's your secondary sealing surface, a means of occlusion, and a means to drive. So, if you see here, this is your primary sealing surface. This is actually the drive ring that actually fixes itself onto your motor shaft, or onto your motor shaft. And then if this right here in between is a whole piece of in this case probably silicon carbide or carbon, but your front area here is highly polished, known as a lapping process. Years ago, when I first came in to this industry, you would take the mechanical seal and flip it around, right, and polish that side and reuse the seal. Now these guys got smart, right? Now they cut a divot on the back end of the seal. Or also we used to lap it. We used to get a marble block, repolish those, and it was a skill unto itself. That's gone. I don't know anyone who relaps mechanical seals, but that's what when I started, people were doing. So this fixes on. This is actually polished. We have our mating ring. This color here. This is most likely a ceramic piece. So you have your primary, and usually your stationary seal face is a harder material. So ceramic. You see here, this has an O-ring on the outside that helps it fit and remain stationary. And this spring, this is the means in which we make sure that the bolt surfaces remain in intimate contact. And in these technology, what we're using is 1 microsiemen of fluid to get in between those two faces, and that's what creates our seal, and keeps the seal from not leaking. So obviously, depending on your fluid though, if you have abrasive material and whatnot, we need to be aware of that to make sure that we're selecting a seal that is the material to allow it not to wear or break down from abrasion, chemical compatibility. We have all different. I could do a class for 4 hours just on mechanical seals, so I'll try to. But some of the tougher applications we do flushes, pot plants. I mean, I could go in. That's a whole class in itself. So let's keep it to the basics. So there's actually 2 main categories of mechanical seals. They're known as a pusher or a non-pusher. Very easy. One technology is static, and the other one is dynamic. So that's the best way, just like pusher and non-pusher. So a pusher seal will employ a dynamic secondary seal, typically an O-ring, which moves actually with the primary sealing face. The feature compensates for seal face wear and wobble. So basically what that is actually this seal that we were looking at right here in this design. So we have the spring that always pushes the 2 mating surfaces together. You can see here. This is your stationary with our O-ring. That's pressed into the pump. This whole assembly here is riding onto the motor shaft, or I should not so much the motor shaft, but a driven shaft. So this would be fixed. This is usually a collar that you screw onto the shaft to set your distance. You have our spring. We have an O-ring to help make sure that stays nice and sturdy on the driven shaft. The spring pushes that into contact with your stationary seal. This is probably the, most common, type. They usually call it a type 21. You might see that in paperwork, a type 21. Seal, most common, most inexpensive. Disadvantage though is, you could have, secondary hang-ups, and you'll see that, through use, the shaft, you'll see this a lot, the shaft gets fretted, scored up, which is not a good thing. So what the pump manufacturers did on that is they started introducing, instead of the drive shaft being a solid shaft, they put in shaft sleeves. So basically they mic down a shaft and have a sleeve over it. So that way, instead of the operator replacing the whole shaft, a lesser dollar component is replaced on a repair. So then the next one is your pusher. It basically uses a bellows seal. Typically, the bellows seals can be a couple of different materials. One that I typically see is a PTFE. So they're typically good for like chemical applications more with this type of seal. So basically, on the case with these, it looks somewhat similar. There is no spring here. This is a static. This would be a static seal. So we're going to have this fixed, same as you see on the others. So you got your collar, your station. Every seal is the same. The only main thing that's different is this. It would be a bellows type, and we would include this completely and hold the two sealing surfaces again in intimate contact. But you wouldn't have the dynamic changes, especially if you have some flatness or wearing. You might have more of an issue with abrasives with this than you would have like with the dynamic or pusher seal. So main advantages, handles high and low temperature applications, not prone to the secondary seal hangout like the others. Disadvantage, this style seal is that it thin bellows across the cross sections, must be upgraded for use in corrosive environments. Kind of what I was telling you there. We can get that in a wide variety. Chemical applications, I can get that into a PTFE type bellows. Some of the other configurations that you'll see out there are double mechanical seals. So if we're trying to seal off two surfaces, so if you have a pump that has pressurized oil on one side, like solid handling pumps, you want to be able to cool. So you have oils on one side that could possibly be under pressure. We want to protect that oil and fluid not to get into the process of the liquid process, and then we want to protect the liquid process from leaking. The other would be seals in tandem. I don't know if you guys do any refineries or oil and gas or anything like that. So what you do is you have two mechanical seals. If the first one fails, you have a buffer fluid with a sensor, right? So if the first seal fails, it sends out an alarm. The secondary seal is protecting from that fluid leaking. So in the cases of highly volatile or corrosive or dangerous chemistry, that type would be used. The other one, and probably today, the mechanical seals companies want to come up with a solution to having multiple components of a mechanical seal. So they came out with the cartridge seal, and basically what that is all the components that you see press fit into one assembly, so they can just plug and play and put it in. And then there's many other configurations and options that we can have. All right, so let's get into curves. So basically, a centrifugal pump curve, we plot it against a known head and its capacity. So head being, could be expressed in feet or meters or whatnot. mind you, a lot of the pumps are European made, so we do run into that, so a lot of cubic meters, hours in your capacity, gallons per minute, liters per minute, so on and so forth. So in this case, the maximum head for the curve of this particular pump is 115 units. I typically would say feet. This is called your max shutoff head. Then you have what's known as your BE point, or best efficiency point. Of this impeller, it's between 80 to 85 of the shutoff head. Now that's pretty much you'll typically see that your efficiency point is about 80 to 85, but depending on the pump manufacturer, that could vary in a lot of degrees, as well as different technologies of pumps as well.
Dave, can you explain a little bit what the head is? I mean, is it the distance of piping after discharge, or what, PSIs, or what?
Yeah, so your head is basically your discharge pressure, how much pressure the pump will be able to produce. So that's, you guys are pipe guys, that's calculated by a couple of different things. What our known energy is on the suction side. So if we have a tank's full of fluid, and it could be 10 feet above where the pump is, I have known atmospheric pressure on the fluid pushing gravity pushing down on the fluid to get into the pump. I'll have a known static pipe run that actually has additional force that will allow the fluid to get in the pump. Then I subtract that by my no friction losses, right? How much losses that I have on the pipe, and then on the head of this. So I take that, and then on the discharge end, I do the same thing. So based on what my flow is, my run a pipe, I'll take out my friction losses out of that, elbows, valves, so on and so forth. And then anytime I go vertical, it's a direct impact to my pressure. So I take those calculations together. Take my known energy on the suction side that will allow the fluid to freely move, subtract it by my known obstructions of flow on the discharge, and when I put them together, I can equal out what my actual discharge or head pressure is required. So, did I confuse the hell out of you, or no? Okay, so that's basically it. Yeah. So basically, your head is how much the pump can develop of discharge pressure.
So how far it could pump the liquid?
Yes. So you can see a little bit different curve here. I'm slowly adding a couple of components. Do any of you guys know what the 13, 12 and a half, 12, 11 and a half, 11 would be in this curve? Anyone want to take a shot?
Yeah.
Impeller size. So, we're taking the same unit of measurement. I guess the overall curve. That curve was for a 13-inch impeller. So the three things that changes the flow rate and pressure capability of a pump is your impeller trim and your speed. Those are your two number one things. I can control that. The thing with a centrifugal pump is if I trim an impeller, I reduce my ability to generate flow, but I also reduce my ability to generate pressure. And that's the same thing with speed. If I reduce my speed, or the RPM of the motor, I reduce my flow and I reduce my ability to generate head. When we get into positive displacement, that's not the case. So I just want to point that out now. So you got three different, and you got multiple different impeller size, which is typical to any pump. Notice on the bottom here, see we got 10 and a half. You see that gap, that low flow, 20 gallons per minute, or capacity 20, 30, 40. That's what I was talking about with the peripheral pump. Just on principle, that's the toughest area for a centrifugal pump to hit. And if you're riding so far to the left or so far to the right, you're moving too far away from your best efficiency point, that the pump becomes inefficient and potentially would wear a lot faster than the pump that was selected right for the application, which you see all the time. Then on the bottom is actually a curve for our horsepower. Now, if you notice that the horsepower curves correlate with the impeller trims. So that allows us, when we are plotting, if we're plotting a known head, say, in this case 60, and we're coming down and we want 60 feet, 40 gallons per minute, this curve allows me to dictate what my horsepower needs to be and what my trim of the impeller needs to be. So in that case, it would be like something like a 7.5 horsepower with a 10.5 inch impeller trim.
When they trim the impeller, that doesn't do anything to the housing itself. It's
No.
an open area. So
Correct.
basically, like 5 years ago, the guy's requirement was 500 gallons a minute. Now he needs 1,000 gallons a minute. Just swap out the impeller
Well,
for
well, it all-
horsepower and
That's it.
everything else comes into it.
well, that's a great question. So typically, I would say, yeah, you're probably in a new pump at that point, but it all depends on how they originally designed the pump for. Okay? Years ago, VFDs, right, were when I came in, VFDs were the size of this wall, right? Now they're the size of your hand, and the price points are just, night and day. So, people now can take a pump, oversize it, slow it down by speed, benefit from the reduction in energy cost, and then have the capability to then increase the speed of that pump if their demand goes up, okay? So it all depends on that. We're able to do that. If that's a consideration that they want to make, to look at things not just on the short term, but on the long term, we're able to design and put a package together that allows them to increase. Typically, you would still fall in, so, say their capacity today was at 40 gallons per minute at 60, and they know at some point they're gonna double it to 80 at, 80 gallons at 60 or whatever. You have to have that within the range, because, once you start replacing your casing, you're replacing your piping, it makes no sense. You're replacing everything at that point. So there is limitations to that, but if that's a thought process the customer wants to go down, yeah, we can design, we can put that in before.
So Dave, if you go from a 7-inch impeller in that pump to a 6.5-inch impeller in that pump, what would need to change? Obviously, you need to change the impeller to the 6.5-inch, but would you need to, is that the only thing you need to change?
Yeah, it would. The only things that you would have to figure out, and I guess we can get into that, is how you have what's called the MPSH requirement of a pump. And that's that, when I talked about that suction side, that known energy that allows fluid to flow into the pump. So a pump requires so much energy on the suction side of that fluid. So as we increase it in impeller, we increase that requirement. So we gotta make sure that that's fine. Two is if you increase flow, you increase your discharge pressure. So you gotta make sure that, your piping arrangement and your pressures are in line as well. But theoretically, as far as to increase flow immediately, yeah, you just replace that impeller, remove the casing and put the higher size impeller.
Is everybody comfortable, they know what horsepower based off the impeller in there, how to pick what that is, with that chart?
Dave, you said it was like 10 horsepower. You base that on where the best efficiency point is for that 60.
I
60
just-
feet ahead?
I just picked a number, but I mean we could throw any numbers out there on that curve. So pick a capacity, what do you wanna operate at, Dan?
60 gallons.
Okay, so 60 gallons, and what's your head pressure?
50. Or 80.
Okay. So we're 80, we're gonna come over to your point 60, so we're pretty close to the best efficiency point. Now, the best efficiency point is our goal, that's where we wanna hit. Rarely do we ever get there, we wanna get as close as there, but you know, don't be concerned if you don't get there. Alright, so what I do know plotting this automatically is I'm at 11.5 horsepower, okay? So I come down to here, I know this is 1, 2, 3, 1, 2, 3, so I'm at this curve, so I come down to my 60, and then I plot this back here, I'm roughly around a 20, probably a 25 horsepower motor. So 11.5 trimmed, impeller trim, and a 25 horsepower motor to do that application. Now, mind you, curves are typically into two different speeds. So your basic motor speeds are 3,500 RPM and 1,750 RPM. So, you know, that would be also typically stated somewhere on the curve of what your operating speed. So then when you go get your motor, your 25 horsepower at 1,750 50 RPMs or 35, that's how you would pick that.
So you're talking about oversizing too. Say I have that, and my capabilities are going to double. I'm putting another line in that this pump is gonna work both lines. You know, supply both lines.
Mm-hmm.
So with that said, how would you oversize that?
Okay, so one of the things that we do to oversize that, so the first thing I would take a look at, so he's got an application at that, what did you say?
60,
60 at 80,
yeah.
okay. So first thing that I would do is say, alright, let's try to accomplish this application by going with a max impeller. Okay, so if I go with that 13-inch impeller, I'm a little too high to what his point is, right? So his point's here. If I go with this, I'm way over here, right? I'm not hitting this point. So there is a way I can do that. The way I do that is then I calculate speed. So this curve is at a known RPM. Say this is a 3,500 RPM curve. So I go with my 13-inch impeller. I say, let's operate at 2850. And the 2850 actually moves everything to the left and down to the left because I'm reducing my ability to generate flow and ability to create pressure. So by reducing my speed, I could probably get to this point with a max impeller. And what that does for the customer is that long term, he has the ability now to adjust his pump and increase his flow. The other thing is if I'm hitting if I'm trimming, I'm selecting a pump, I'm trimming the impeller at whatever known RPM, he's not going to have much adjustability in the pump. So might be desirable for the customer to want to have wiggle room.
So what horsepower would you use with that then? Same horsepower, 20?
Well, that gets into more of an interesting thing. Okay, so if I reduce my speed and I hit that point, that 80 at 60, I'm at 2850, I reduce my horsepower requirement. So I'll actually be operating at that 25 horsepower at that point. So two things. Some customers desire to reduce their energy consumption, and I'm not a proponent to this, but I occasionally get into it where they're more concerned about reducing their energy, that I'll fix that 2850 with a VFD now becomes a fixed speed, requiring them just to get a 25 horsepower motor. If you're going to do it right with the vision of long term, then I would then reselect the horsepower based on my curve, which looks like would probably be around a 40 horsepower motor. So,
Yeah. And obviously, what you're talking about is some people, they look short term because it's a less expensive option. So if you're going to go with a 40 horsepower motor instead of obviously a 25, there's some additional costs that go with that. So that's you know how companies are. Sometimes they don't want to spend the money now. They rather just wait and do something down the road. But the right way to do it, like Dave says, is just if you know you're going to expand the line or put another line in that's going to be fed by that pump, you know, is to go with the oversized, you know,
Now-
oversized motor.
If you got a closed couple design, you basically the customer is somewhat screwed, right? But if you got a frame mounted design, that motor and the pump is two individual components, right? So it's not difficult for the customer to say, hey, I'll maximize the cost of the motor for the next 5 years, and if I have to get a new motor, you know, big deal. And it's all up to them on what solution they're trying to get.
So what happens on a pump curve? Customer tells you got 100 gallons per minute at 30 feet ahead. Turns out he doesn't have, I mean, he has 30 gallons a minute at 100 feet ahead. Turns out he only has 40 feet ahead. What happens when they put that pump in? You sized it for 100 feet ahead, you know, at 30 gallons per minute. They go to throw that in there. What happens to the motor?
Yeah.
What happens to the whole application?
And this, you know, and what, you're talking about a typical example that happens, and one that I always, I don't know who you're going to show this to, but a lot of the engineers miss. A lot of the concept of what happens is a lot of engineers just don't think that way. So with that, Dan, do you want to take this because you had this you had this happen at we were actually at a account in
Yeah,
Pennsylvania, and boy, the engineer was very pissed at me.
Well, you
Okay.
get something.
But-
Well, it's bigger. It'll work,
Yeah,
and that's not.
well-
It's not the case. I mean, that's.
So what he's describing, right, is this. So hey, we sized this pump for way out here. You know, the head pressure up here and whatnot. Okay, so we're shooting for the max, 115. Okay, but the customer really only needs 60. So theoretically, you think, hey, no problem, the pump can handle that because I can do 115. No, it doesn't work like that. Why doesn't it work like that? Okay, so what happens in a pump is as our load is predicated on the fluid that's transferred through the pump. So as we reduce our head pressure, okay, so we got this 13, we're shooting for this, and then our pressure, right, our pressure is dropping. So what's happening as the pressure drops? Now we're operating over here. What's happening? We were operating at 20 gallons here. We're now operating at 80 gallons. So as the discharge pressure drops in that piping system, the pump puts out more and puts out more and puts out more flow, okay? And then now I'm operating here. Before I'm operating here, boy, I had this 15 horsepower motor. Not a problem, it was love and life. But when I'm operating out here, oh boy, I need a 40 horsepower motor. And that motor is burning out, tripping, and failing. So to get back to the little story here, so we were at an account, and the guy purchased a pump, and the application was probably right around 30 gallons at 15, kind of what we're talking about here. And we get there, and the motor's tripping out, and something's wrong. Looking at this thing, and notice that it was like a 7.5 or 10 horsepower motor. And I'm like, boy, this doesn't look good for this loop, right? I'm like, get me the curves, and get the curves. And I pulled Dan aside, and I started yelling at him. I'm like, did you do this? Right, remember that? I'm like, did you do this? Did you select this pump? Because it was 100 and something feet, and the loop he was showing me was up 20 feet, over 5, and back down. I knew that was the scenario, that we had a pump that was sized here, so the motor was tripping out and failing, okay? So I almost wringed his neck, and then I talked to the engineer. He's like, oh no, we're just testing. That's the real applications way over there. And I looked at him smiling, and I said, all right, let's have fun with this then. So we went over to the pump, so the first thing that I did was I closed the valve. Okay, if I close the valve and generate back pressure, I turned the pump on, and the pump turned on, and I slowly creeped the valve up. The pump ran fine. And I turned around and I started walking away. Like, you're good. And he says, we're not good. What did you just do? I said, well, you know, I had to generate back pressure because you don't have enough. And he couldn't understand what I was talking about. And I tried for about 25 minutes, and we got calls 2 weeks later and 3 weeks later trying to rehash what's happened. But that's exactly what happened. So if you have, and you know, engineers are very good. New projects, we go through this all the time. You guys know what an office plate is? Yeah, okay. So we do a lot of projects in the engineering firms. The last thing you really want to do is undersize a pump. That's not a good thing. So you gradually oversize. So they'll go through the design, have their flow rates, and say, all right, tag on 15%. Okay, tag on 15%. Somebody else, another engineer looks at it, hey, well, let's tag another 15%. Rule of thumb, we don't want to be short. Tag on 50. So you go in the projects, you put the pumps in, next thing you know, they're all, you know, don't have enough back pressure. So I sell a lot of office plates to compensate for that early in projects, and that's usually the #1 issue.
So,
It doesn't make sense that you put extra load on the pump and it takes less horsepower.
Correct.
But it has to be in its curve. So a lot of times you'll see a butterfly valve after the pump where they can kind of dial that in, and that's something we have to communicate with our customers. You dial it in to find your maximum efficiency for that pump, and that can make a huge difference on the curve and what's cost to operate in that pump per year. You want to get that dialed right in. You know, so if you have a butterfly valve and a pressure gauge, and they can check with amp draws too on the pump to see that we're dialed right in. So it's kind of hard to understand. We're loading the pump, and it's going to take less horsepower.
Right.
But that's the way it works. And a lot of guys, maintenance guys, aren't going to understand that. And that's what we need to. That's where we can come in and solve problems. You know, all you need to do is put a butterfly valve in here, an orifice plate, or whatever, to get this dialed in. So it's good to read curves and see what's going on.
Is that similar to like a circuit setter on a hydronics heating loop? Like a butterfly throttling?
Similar, yeah. They're doing that based on flow for heat transfer across that is what they're doing for that. That has a lot to do with temperature and everything on circuit center. So, but similar, yes.
I had a question, looking at the horsepower again, like Dan said, you go with 60 gallons per minute, and I forget what he said. 80 foot ahead. You come down for your horsepower. What you stop at that first line, the top line. What are all those other lines?
They correspond with the impeller tray. So the bottom one would correlate with the 10.5,
okay.
11.
Six lines up top, 6 on the bottom.
Okay.
Sometimes the horsepower, which makes it easier for me, is when it's laid over on the curve and you can kind of follow it right away.
Right.
That's a little bit easier to, you know, so.
Yep.
Yeah.
Yeah, good point. So, yeah, what he's saying is that this horsepower lines, a lot of times are on that curve at the top together, so you can plot it that way.
I just thought that was Greek. I didn't know what that was.
Well, I'll send you a copy of this presentation in Braille. Well, any other questions on that? And I'm glad that you asked that question because it is one point that I want to bring up is that that this is the only condition in which you would overload a motor or overload, have a higher amp draw on a motor for a centrifugal pump. Is this scenario? All your other known failure modes are under load. You have a low amp draw. If I'm cavitating, and cavitating's pulling air bubbles into the pump, or I have entrained air, or if I have other issues, it reduces the amount of flow that gets through the impeller, and it reduces my overall horsepower. So you see that on the flip. So if you see something and they're talking about high amp draw, two things. You're either running into not enough discharge pressure, or the pump's undersized, or something like that.
And I say, when you see a pump and it's got a gauge on the discharge side, that's key information there. I mean, that can help you size the pump so much. I mean,
And you guys being piping guys, I can't stress this enough, is that I go into places and they don't have any gauges. And if you don't have a gauge on your suction and a gauge on your discharge, you don't know what's going into your system. So the best thing you could do is when they have a project, say, you know, you really should have gauges, you know, gauge guards or whatnot. So that's definitely an important factor, or else you're riding blind. For me to help somebody out or them to help them to troubleshoot their system, you know, riding blind's not fun.
You mentioned VFD, that's variable frequency drive,
Correct.
and that's what you slow a motor down to that 2850 you're talking about?
Yeah, so motors are typically 60 hertz,
Right.
mostly European. So yeah, we control the hertz from 60, and we can reduce that down, which correlates to the actual
RPM.
speed of that shaft.
Is that like is that right on the motor, is that done remotely, or
Well,
how's?
you know, these days, the push in our market, at motor market, is instrumentation integration. So you are seeing motors that have drives mounted right on it. Typically, it's an accessory component that they put in. So here's an actual engineered curve that I have, and basically it's the same thing that we've looked at. The only difference is it includes the MPSHR. That's the requirement of the pump. Again, that's the energy that's coming in on the suction side. So the rule of thumb is the net positive suction head available minus the known vapor pressure, and then all liquids have a known vapor pressure. So we can get it, I don't want you to get too hung up on that, but we subtract out the vapor pressure of the product that we're pumping, and basically the MPSH available needs to be equal or above the MPSH required by the pump. If that's not met, we get things called cavitation. Cavitation is when we have, we're pulling air pockets into the pump, and those air pockets will get into the pump and get into the eye impeller and explode onto these veins, onto the eye, and basically when they explode, they rip material right off the pump. And what you'll see, it's the failure or the condition is called pitting. So when we take off a casing, we'll see these pit holes all over the place, and you can hear the pump operating in this condition because it sounds like it's pumping marbles. You'll hear ping, 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 and that's exactly what's going on, and that's means that they're not meeting this requirement. And some of the things that we could do for that is slow down the pump, increase the height of the fluid he has on the suction side, put pressure on his tank, or anything we can do to make sure that he's meeting that energy requirement into the eye.
Everybody's good on
To build up the
MPSHR?
pressure,
Yeah.
right, Dave? To build up more
You
pressure?
have-
into
But
it?
available has
Yeah.
to be equal
You
or
have to have
higher
enough
than
going into that
required.
pump to get the certain output, and the more output you want, the more you have to have
Going
going into it, so.
And if you
You know.
pressurize the pump, then that would also take care of the same thing you were doing with the butterfly on the discharge, right, for that motor?
Well, not pressurize the
No.
pump, but you
Or pressurize the tank.
Tank,
Put
yeah,
pressure,
put more
right?
pressure
That would do
on
the
it.
same as the valve.
No, you're
No?
still off your curve then, because you
Okay.
gotta keep back pressure, so you're in back
Yeah,
pressure there.
two different
Okay.
things. Yep. The at the beginning I said, hey, the goal of a centrifugal pump is just to add velocity, right? And the important thing is that the pump requires, unless it's a self-priming pump, it requires energy that coming into that pump for it to work properly.
The more energy you get coming in, the more you get going out.
Correct.
Too, so even if the curve, you have more MPSHR, your final curve will be higher then too. So-
I had people call me on applications and they say, yeah, I need a pump 3 gallons per minute. So what's your pressure? Whatever. Yeah, let's get a bucket then, and just dump it upside down, is what he's telling me. You know, fill a bucket up to 3 gallons and just dump it out, because there's no known energy there. If I take a bucket and I have a 1/2 inch piece of pipe, and I run it, 20 feet down this building, right? I pour it in, that water's gonna go to a certain point and stop. That's your MPSH, that's the best way I can describe it. That's the energy that we're using and needs to be required for the pump to operate effectively and correctly. So you can see here, same thing, it plots down. You get to the engineering curve, they get a little bit more specific, 4.9375 inch impeller, so they get to dial it in pretty good. But this curve is just like the others, they're giving you more of a range. This is typically what you see on an engineered curve. Some of your, like you said, some of the others are different. But here's your range. So this pump's able, impeller range is 5.1 inch impeller to 3.9. Our application in this case looks like 75 gallons at 85 feet. Okay. So what we have on this is they're saying, hey, to get this, you need to operate at this trim size. They're showing us, hey, the best efficiency point for this pump is 59.9. This is a mag-driven pump. Mag-driven pumps historically have a lower efficiency point than others. Then what we have here is our efficiency. So this efficiency curve is telling me that my max, where I should be operating, my impeller trim, and then mid. So it's saying that my efficiency point on this is about 55. So I'm 55% efficient, and the max I could potentially get if I was in the best point on this pump is 59.9. So for me, that's good. That's a good spot to be on there. If I come down, it's telling me, hey, I need at least, just about 5 feet of MPSH available in my piping system. I need 5 feet of energy, okay? Atmospheric pressure is what, 14.9? So typically if you have a tank, you're probably pretty good. And then you come down here, my max, and then my design point is telling me my horsepower would be around 3 horsepower for this pump to work.
59.9 is gas per minute.
Nope.
No, that's
That's
6%
your-
efficiency.
That's efficient.
That's efficiency, yeah. You're thinking, well, man, 60% is not that efficient.
Right.
Your centrifugal pump, it's slipping, so, I mean,
Yeah.
that's good efficiency, so.
With this, and this is actually a metal mag drive pump. So one of the things that actually brings that down is a thing called eddy currents. So when you have metal insulates heat. If you're generating high heat, it reduces the overall efficiency that you have out of the pump. So it's not, this is a lot lower than the majority. If this was a sealed centrifugal, we'd be around that 80, 85.
Everybody knows what a mag drive pump is?
I've seen it, yeah.
Okay, there's
In
no,
Omag,
there's
yeah.
no direct shaft connection between the motor and the impeller, okay? There's not a one-to-one coupling or anything like that. It's magnetically driven, okay? And that's the only mechanical seal that, because it's not connected, yeah. Use a lot of chemical applications where they
In
can't risk
Omag.
leakage.
What's his name, Alpha Lau was here and showed that one in the bottom of the tank.
Yeah,
It's probably
I,
in the mag. Oh, yeah, that's, yeah, exactly, that was a mixer, that wasn't a,
Right,
that
right.
wasn't a pump, that's a
Same
mixer.
person, same
Yeah,
person.
exactly.
let's see if I got some here. Cause I noticed afterwards that I was missing, mag drive. Alright. Mag drives are also offered in both frame mounted and closed coupled. Typically closed coupled, but this is a frame mounted. Alright, so This is a sailless pump design, so no mechanical seal whatsoever in this pump, okay? What we have here is, so you got your motor, your flexible coupling, this is your bearing assembly, just like the frame mounted that we talked about before. But this drive shaft is now attached to a magnet. This is a magnet right here, okay? And in that round assembly is, you know, about 8 to 12 magnets that are embedded in this circular assembly, okay? This is your impeller. Your impeller has, your impeller shaft is attached to bushings or bearings. These are usually silicon carbide or carbon bushings. And then this impeller is attached to your impeller shaft. And that's attached to another magnet, an opposing magnet, okay? So when this rotates by the motor, okay, the impeller, this magnet rotates along with it, allowing the impeller to spin. What you have here is this, in between, is actually a closed containment shell. So this whole thing is enclosed, so there's no way for the fluid to seep out unless that containment gets breached. So magnet here, magnet inside, turns, that's a mag drive pump. In the case if this was frame mounted, this whole bearing assembly would be gone, this motor would be pushed up to here. You would add an adapter flange here, it would be pancaked together, but the same principle. The guys all make sense to you?
The major advantage of that would be why people use a mag drive.
No, yeah, okay, so, lot of advantages with mag drive. One, closed couple design, right, no alignment issues. Two, chemistry, chemicals, no leakage, the pump fails, it doesn't leak. Some of the downfalls with it is you really, this isn't a solid handling pump. So, by replacing the mechanical seal, we have bearings. Now, these bearings are actually in the path of the fluid. We're using the fluid to lubricate those bushings. So if you get solids and whatnot, that's a problem. Great for temperatures. I can go up to 185 degrees F in these pumps. Solvents, great solvent pump. Solvents, ethanol, alcohols. These pumps are really, people like those, especially no spillage on those applications. Sulfuric acid, caustics, chemistries like that. We can do Teflon line, I heard you said. Inomag. So Teflon line design. Well, that's your hiccup is you are now putting your main bushings into that process fluid, so you gotta be particular. Now, pumps can pump solids, but solid is a very wide term. What's the type of solid, if we're gonna do that? But theoretically, we're using that fluid, and we're sending the fluid down through the pump to lubricate everything, so we try to stay away from solid applications. Sometimes you run into it. We have like lime or brine solutions or whatnot that crystallize. So some of those we'll do with this pump, but we don't want anything that's overbearing. So some of your basic questions that you should be asking on any application is, what are you pumping? What's your flow rate? What's the discharge pressure? Temperature? Does the temperature vary? Specific gravity of the fluid. The specific gravity is going to impact your horsepower. So it's definitely something we need to know. Mind you, all your curves on any pumps are based on a 1.0 specific gravity, that's water, okay? So anything that's heavier than that, we need to compensate for. What's the viscosity? Is the product abrasive material? And then I always like practical application knowledge too. What's been working in your plant? What material is known to work? What are you guys using for sales? Are you having issues with sales? Unhappy with sales? What type of drive is desired? Does it need to be explosion proof in this area, or non-explosion proof, or chem duty type motor? And then is it a flooded application? Do we have that energy we need for a pump, or does it require a pump that is able to prime itself? And then what general options are needed with a pump? The other thing, and it's not here, is the general applications. I mean, our job as salespeople is to understand what the true need of the customer is. When we identify the true need of the customer, we're able to at least, sell them the right product and have a higher chance of obtaining an order. So, need assessment. What is his true need? What is he trying to accomplish? And how can we work together to put that solution to that customer?
Dave, are these questions that the customer should be able to answer?
Yeah.
And if
Yeah.
they can't,
Yeah.
that's the some. And if they can't, are they questions that, is there a way for us to figure this for them?
Sometimes you can answer if the product not sure, well, I think it's this, they'll have an MSDS sheet on it.
Yeah.
Ask for the MSDS sheet. That's gonna give you most of it. I mean, they have to have that in the plant somewhere.
Yeah.
And you're always gonna get, that's just water. It's just, well, it does have a little bit of chlorine in it. Well, that's a big difference. I mean, so.
They should.
Okay.
They should be able to, yeah, you run into it. I don't wanna scare you, but there is points where you recognize that maybe this individual doesn't know what he's doing, and sometimes that's.
Really?
I'm telling you though, sometimes that's harder to figure out, right?
Yeah.
You go down a path and then you realize, wow, I think unknowingly as salespeople, we go into their environment and think they know what they're doing, right? We take that just on face value.
Right.
And it's through the questions and trying to identify what they're really trying to do that, at some point we gotta recognize if they're confident,
When you're asking for like viscosity, I mean, are you looking for specific, like, cause I think people say, what's the consistency of this or that, or do you want like,
Yeah,
what centipoise or whatever it is?
Yeah,
Or, I
if
mean, are
we-
you that specific?
Yeah,
or-
yeah, I'd like to get the centipoise. I mean, obviously, if we know it's a water-like fluid, pretty easy.
Somebody
Yeah,
asked
milk,
what kind
you
of
know,
base
you know what
stuff
milk,
Yeah,
yeah, it's
dilute.
common stuff.
Yeah.
Honey,
Or you get syrup, corn
Yeah.
syrup, or what's
Honey,
the,
yeah, it's
it
like-
just is in the country. Oh, it's got some sulfuric acid. Okay, is it 10%? Is it
Yeah.
50%? Is it,
But like sulfuric acid, so sulfuric acid, we're going from 1.0 on the curve to 1.4, 1.6. So what that does is then I have to compensate on the motor. So and that's the specific gravity, not centipoise, but yeah, if it's a non-water-like fluid, yeah, I would try to get as close. So,
I have some charts too that can show you different.
Standard
products.
oils you have different based on your temperature,
yeah, what temperature you're running at.
Yeah.
That's a key. I mean, like eating corn syrup, different temperatures.
Yeah.
Now you're not pumping centrifugal, but.
So I'm about to go on to the next. Do you want to have a break now? Would this be a good time to do a break? Or?
Wanna take 5 minutes, guys?
Yeah.
Keep it
Yeah.
up? Okay, let's do 5 minutes.
You talk to Wes from installing at all? Okay, you say you got my email,
I
right?
got your email.
Okay, that's just,
What's the date? January
like-
6th, 4th, something.
it's a little later, it's after our, AD.
We got the white here.
I think it must be in the emails. I wanna say it's,
That's the way it came from.
was it the week of, I don't remember, the week of the 13th or the 20th. I have to look at my emails.
Which was
It was either the week of the 13th or the week of the 20th. I have to look at that. Because what he wants to do is, he wants to, like, you for a day, me for a day, and also do a little bit of training in the warehouse. And I don't feel like State College for a day and do some counter training. So he figures he need, one day Scranton, one day Williamsport, one day State College. Plus he comes in all the way from Chicago. So I guess if he drives a day in and a day back, so that's the week. So I guess we're looking at like Tuesday, Wednesday, Thursday, and I guess he's got Monday and Friday probably as his travel days. I have to look at my computer though. That's where I have it. I thought I had it written down here.
Yeah, I always do. It's one of those things for me.
You don't use it for a while.
Until I have to do it to.
Exactly, that's the,
'cause
it's
like-
always good, and if you can go in there and help solve some problems with sizes of pumps and figure out what's going on, there's huge cost savings
Good,
in pumps. If you can get them in the right pump, the right curve, and everything, you can save them, and you can show it to them, cost savings per year. You know, the pump, if you do it right.
Right now, I'm got huge do it elsewhere. I even had turned it a year ago. We still don't have it working. So small huge changes, so I'm not.
Oh, goodies.
Yeah. Do you find helpful, what I find helpful is out there, besides getting that information, I'm gonna talk to you guys about a pump, is do a sketch of everything with the footage and, it's 12 feet up, 100 feet across, size of the pipe, just put it all in there, give you a little diagram with it.
Absolutely.
Okay.
I do that just to allow my brain to work. It's one thing,
I even bought a new regulator.
Yeah.
I think a lot of times, I noticed, early on, you're kind of nervous, you're trying to substantiate why you're even at this plant,
Yeah.
And if you slow down, ask, you can't, I think customers actually like the fact that you ask more questions and just take your time and do it right, put the sketch together, walk through, I do
Yeah.
that pipe walk, you guys do that probably more than me. I do that pipe walk, where's this going, where am I, let's do this together and work it through.
Does that
Yep.
go up after that?
I know what you're saying.
It's down into that and straight from.
And that goes back to DA
right
tank?
after the.
Like that, the DA tank?
Yeah.
So you know, the back pressure, you
You
couldn't have too much, you couldn't have. too
Tom,
much
I was talking
pressure
to
in the
one of the
control
guys
back
from
there and what we're doing.
Shadler Yesko was up at the
There could be
Scranton
a trap
office,
below and downstream
and I
somewhere.
noticed he had a
And then
Sonata
that return
hybrid.
line, 'cause you already have
And I
17
said to
pounds
him,
coming in.
realistically, what are you getting for mileage? He said, Highway 36
So they could isolate. take the
and
regular
pound
out,
34.
maybe two.
Yeah.
He has the
So,
3/4.
he said, yeah, and he said, most of my driving, he said, is around town, so that's where I really make
And
it.
that's when
pretty
they
good.
putting 3 pounds of steam through. But that's enough to keep their office warm.
You have an uncle
You
that
get
got
too much
one,
pressure in
seen
your
it,
back,
heard it's
that's the
red.
problem, there's too much pressure in the
Yeah.
pressure return line. Can he let that off the steam track, they put a drain somewhere and just drain the condensate down and see if it works?
Hey, Henry,
You can just open it up.
all right,
No, off of your steam trap, where it
Okay.
comes down, it goes to return line
Now
now?
it's right into, there's no valve after the trap. It's right into the,
But is there a place you could drain it then?
after getting the condensate return line?
Yeah, I mean, could he take the trap down, is there a drain, a physical floor drain or something?
I'm sorry.
He can drain it,
So-
I don't know.
or dump it.
to do the 3-inch.
I think he's
Okay,
got too much back
yeah,
pressure
just,
in that
because I
return
think we
line.
have that down here where I am.
He can't
Okay,
overcome that.
so we need to head to do
With
the
the regulator
3-inch.
at a couple
Okay,
pounds. What's that?
give me a minute and I'll call you back,
Trap's
right?
flooded all the time, basically.
Exactly,
All
you
right,
can't
thanks.
you only have, whatever, 3 pounds, 5 pounds, or whatever here. And if you got 5 pounds of back pressure, you're not gonna move it in your return line. Now, you could have a trap blowing into that return line downstream and keeping pressure on that. Or the line could be sized too small, and even everything is turned in there, steam splashing back and create back
Or
pressure.
the return, or the.
The return line going back to the DA from there. If he disconnects, well, but still, even a trap blowing in there though, you could have back pressure.
Down.
Yeah, I mean, he can put a gauge on that return line and see what pressure he's got there in that condensate return line. If he's got 5 PSI, he's gonna put 3 PSI in there, it's not gonna move it. You know what I'm saying? You can't get
He's
past it.
getting 3 PSI because he has the bypass open, because it won't go through the regulator. He has 17 pounds coming
Yeah,
into
well-
that regulator, well, the regulator won't open,
Right.
and
You're
that's the
just,
steam through.
you're just locked, I mean, just.
So that's why he's got the valve shut, the regulator, and he's just running across that bypass. But 3 pounds is keeping the temperature they need for the office, so.
Well,
He
maybe
was
the
asking if
regular.
the regular is too big. Should he have just put an O or something in there instead of that
How
great
full
big
size was that regular?
inch and quarter?
You don't know what your pounds per hour are or anything.
I don't know who sized that. That was there when
Well,
I
it could be
started
way too
calling them.
big, yeah. It
They're,
could be way
they're
too
getting
big.
really frustrated. They rebuilt it and they put it in, I don't know if he bought a new pilot.
It could be just way too big, too.
He has
What did Joe say?
Well, we didn't even talk about the trap last time because it was out when we got
Did he think the
there.
regular was too big?
And no, he didn't seem to think so. But
I
he
don't know
priced
what
them
the
on
load is,
rebuilding the
like, the load.
regulator and new, and it was only $200 more for the new regulator, for the new regulator. As soon as they put it in, turn the steam on, it's still out there.
It's hard to tell without looking at it, still, I mean, just did you try to bump the temperature up to see if it opened? I mean, it's a temperature. pump.
Dave, where are you from?
It's not a pressure
Hey,
pump.
Massachusetts.
Well, I knew that much.
Over,
To make sure it's open,
I live over in Sturbridge, Mass,
There's
right
nothing
on,
wrong with the regulator.
right off of 84.
Is that on the
Getting
what-
frustrated, it's cold now.
West side?
It's actually